Okay, we take the Newton's method as an example to show how to solve a minimization problem for univariate functions. So by univariate functions, we mean that this function f is a mapping from real number to real number only. Okay, so it's not n-dimensional Euclidean space, it's just n equals to 1. Okay, so in other words, this function can be simply draw. If you like, you can draw the function. It's just like this. It's not in a high dimensional space. So we'll try to minimize a function, univariate function f. Suppose we don't have any constraint. Just let's try to solve this f. Okay, so recall that I think you all know this Newton's method from calculus. So Newton's method is a way to find a minimizer of a given function f, univariate function f. The idea is that suppose we know that function, suppose we already got to some point xk, and that is you can say this approximation of the true solution, and we want to further improve it. And the question is, how do we improve xk to get a new approximation of this true solution? So here, let me show you the idea. Suppose I have this as my function. Okay. So this is the x, and this is the y value or the function value, and then you have this function, for example. Say I have this seems to be the true solution x star, which we do not know. We want to find something with that we want to find, and suppose now that we're at xk. So usually this x with a superscript k, this notation means that is the solution is the iterator we got at the case iteration or case step, and then we want to get to find a new point. So we want to find a new point that is a better approximation of x star than the xk. Okay, so idea here is that Newton's method is following this idea. So at this point, I know I can calculate the slope and slope of the tangent line, and also the curvature here. So in other words, at this point, I want to use a quadratic function to approximate this function, this entire function f here. So this is the f, but at this point, I want to use a quadratic function to approximate this function f at this point. And how do we mean by approximation? It means that I want to find a quadratic function who takes the same value as f at this point. At the same time, the derivative of this function q, the quadratic function q we want to determine, is the same as the derivative of f. And not only that, the second order derivative of q is also the same as the second order derivative of f. So I want to find this function q such that the q is a quadratic, means that qx is something like ax squared plus bx plus c. At the same time, the q prime, so this is the one thing, and I also want the qxk to be the same as f of xk. I want the q prime at xk to be the same as f of xk, f prime at xk. The q double prime at xk is equal to f double prime at xk. So I want to find this quadratic function such that all those three conditions are satisfied. Okay, and then we can determine this q. That means I can determine the a, the b, and c such that these three are satisfied. So how do we do that? I'm going to write my q in this way. So the q is written as a constant. Remember that for a given xk, this will be a number. There's nothing arbitrary. It's just a fixed number. And also, this is the derivative of f at xk, second order derivative of f at xk. So it's like I'm taking the Taylor expansion of f at xk, and I truncated after the second order term. So this is like a zeroth order term, the first order term, second order term, and there should be additional terms, but I truncate them. I just leave these three terms, and that will be my q. And then you can easily check that this q satisfies these three conditions here. The reason is if you plug in x, you substitute x by xk, then you will see that this will be cancelled, right? This will cancel out, and this will cancel out as well. So the q of xk will be just f of xk. And then you can also take a derivative on both sides. If you take a derivative on both sides, then this is already gone. And when you take a derivative of this, then this part is gone. Only this is left as a constant. And when you take a derivative of the last term, then this becomes, the 2 is gone. The 2 will be cancelled with this 2. When you take a derivative of this, it will be 2 times this, 2 times x minus xk. And the 2 it will be cancelled with this 2, and then you have f double prime times x minus xk. But when you plug in x equals to xk, then this whole term is gone. So when you take the derivative of q and then set x to xk, you will have only this left. So they'll get this here. And similarly, if you take a q for twice, take a q derivative of q with respect to x for twice, and then plug in x equals to xk, then you get that. So now this is the q. This is actually the q I wanted. It is quadratic function, as you can see. It's a quadratic function of x, and all those three conditions are satisfied. So I replaced, or I approximate my function f using this quadratic function, because f is difficult to minimize. It's really hard to find a closed form for this point, to find this x star here. But instead, once we got xk, we approximate the function f using a quadratic function locally near this xk. And then instead of minimizing f, I will try to minimize q. And minimizing q is easy. The reason is we can just set the derivative of q, calculate the derivative of q and set it to 0 and see what it is. So I can approximate, so I know that q is an approximation of f, and I know it's very good approximation of f because at least near the xk is a Taylor expansion of f near there, right? So it's supposed to be a good approximation of f at least locally. And then once we use the q, we can find minimizer of q instead of f. So I'm trying to find a minimizer of this instead of f. The reason is the minimizer of q is really easy to compute. To compute that minimizer or the critical point of q, I just need to set the derivative of q to 0. So the derivative of q is according to the formula earlier, it's just this. Okay, so that's according to the because this is q, so take the derivative of that and set to 0, and then we can get this. And now the next point x can be solved from this. So I just solve for this x. I get xk plus 1. I'll set this to xk plus 1, and you can see that the solution for this equation is just this. Okay, so solution of that is just this. And now I'm going to set this to xk plus 1. So as you can see from the previous picture, the minimizer of this one is here. So this will be xk plus 1. It is closer to x star. Okay, and once we got xk plus 1, and we'll repeat the same procedure, construct another q, and solve for that for the minimizer of that q, and get to xk plus 2, so on and so forth. So I just by this procedure, you can imagine that if we throw in an initial guess, just some x0, my rough guess of that, and then we just progressively compute x1, then x2, x3, x4 using this formula. Then we can get to the true solution x star. So this is the idea of of Newton's method. Okay? So this is called the iterative methods. This type of methods are called iterative methods because, as you can see, once you give an initial, then they will use a formula to generate a sequence, and hopefully that sequence will converge. Okay, so this is a very general approach for all the optimization algorithms. You throw in an initial guess, and your algorithm is a key. The algorithm tells you how to, or tells the computer how to generate the next point, and the computer will repeat this procedure again and again, and it will generate a bunch of points, and hopefully these points will converge to the true solution. Okay. And by the way, in practice, the computer does not really store all the sequence, because once it computed new point, it throw away what happens in before, and then just based on this new point to generate the next point. So it's not like the memory is always you only keep one or a finite number of variables in the memory, so it will not blow up. Okay, so let's take a look example of that can use the Newton's method. So the f, say I have a function f defined as half x squared minus sine of x. Let's apply the Newton's method with the initial 0.5. So just throw in a random initial here, and I will stop when the point we just got and the next point we can compute has a very small difference. This is called a stopping criterion or termination condition. Basically, they are the same name, same thing for different names. So the idea is that if you generate a sequence, you cannot just keep generating this forever, right? You're going to stop somewhere. So how do we stop? It's pretty artificial. We manually set a termination condition. So in this case, we just set it to that. But there are many other ways to set it. We'll talk about this later. But just remember that when you're throwing an algorithm, put an algorithm there, you should let the algorithm know where to start and when to stop. Okay. So in this case, we said this is the x0, and if we want to compute the we can apply Newton's method, then we know that we have to iterate this. So for x0, we use this formula to get x1, and then with x1, we use this formula to get x2. So the key is this two things, right? You have to compute f prime for any given number, and also f double prime for any given number. So let's see, because my f is defined this way, so the f prime will take a derivative of f. You get this first one gives me just x, this one gives me cosine x. So the derivative will be just x minus cosine x, and then we take a derivative one more time, I will get 1 plus sine x. So this is the second order derivative. So once I have the f prime, f double prime, I can use the formula of the Newton's method to generate this sequence. Okay, so the formula will be just xk plus 1 equals to xk minus f prime of xk divided by f double prime of xk. So this is the iterative algorithm, a Newton's method that we just mentioned, and then we throw in the initial guess. So initial guess here x0, 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 and x0, and then compute, and then we'll get x1, which is this. And then with this, we can throw in again. This will be x1, 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 and x1 here, and then we'll get x2. Or compute it and get x2. And to do this, do this, get x3, x4. You can see the number will stop. They're the same number. And then actually in computer, these two numbers have a difference less than 10 to negative 5. So the computer will stop there. Okay, so this is where the function will find a critical point. But remember that critical point is not necessarily a minimizer, right? It could be a maximizer, or it could be a saddle point. Okay, so to make sure that is a local minimizer, remember that we have a sufficient second order sufficient condition. If the derivative is equal to 0 and the second order derivative there is positive, in a high dimensional case, that means the second order derivative or the Haitian is a positive definite matrix. But right now, since we're considering univariate case, so the second order derivative is just a number, and it's a positive definite if and only if it's just a positive number. So we can compute the second order derivative of f at x4. So this is the last iterator got, and we got this number, which is positive. So that means, although this is not exactly the f not exactly x star, but we know that x4 should be very close to x star right now. So if this f double prime is this positive number, then the f double prime at x star is also should be also a positive number. And in this case, we can see that we stopped at here, and this is supposed to be a strictly local supposed to be strictly local minimizer of f, or at least very close. Okay, so the Newton's method can also be applied to do the root finding. So suppose we're trying to solve a function gx equals to 0, and then you can treat this gx as the derivative of some function f. So you treat g as the derivative of function f. Then remember that previously we were trying to find the minimizer of our critical points of f, and now it is equivalent to finding the root of g. Okay, so you just use the Newton's method where you replace f prime by g and f double prime by g prime, and you repeat this, and hopefully you can generate the sequence and that converge to the root, at least one of the roots. Okay, so this Newton's method is very fast in practice, and for univariate cases, this is probably the best way to do. But there's still some people have concerns that the computing the second order derivative is difficult for some cases. So in this case, it's not a big issue. It's just the f double prime. It's easy to compute. But for some cases, the f double prime can be really difficult to compute. You take a derivative once, it's already very messy. And then you take a derivative one more time, you just cannot handle that. So in this case, some people use a so-called secant method to approximate or to replace the Newton's method. So the idea is, say, we need this on the denominator for the Newton's method, right? So there's recall that this is just the limit. This is the limit of f prime xk plus some h minus f of xk divided by h for h going to 0. Right? You just think this as a limit. Let me actually write it down. This is f double prime at xk is supposed to be the limit h goes to 0, f prime at xk plus h minus f of xk divided by h, right? So if you do not, here is prime. So if you do not really want to compute this, and then you can use this thing to approximate that. So what we use that is to approximate this number, we use this. So once you get xk and xk minus 1, which is before the xk, and then you think that these two are pretty close, then this is like this is used to approximate this limit. So the idea here is that this limit is like the second order derivative of f at this point is like the slope of the tangent line of f prime. Okay, and this is like the slope of the secant line at xk. Right, that's the idea. So in this case, if you replace the f double prime by this quantity here, then you can plug this back into the Newton's method. Then you will not need to compute the f double prime anymore. You only need f prime. The only thing is that you need to actually record this number. Don't throw it away when you compute the next number. You have to keep this in the memory, and then you compute this. You substitute this by this quantity here. Then the Newton's method becomes this. Actually becomes this part. Okay, and then you simplify the right hand side, you get this. So this is the Newton's method. This is the secant method. Another thing, another difference between the secant method and the Newton's method is that we need two initials to start, because as you can see, to compute the next value, you need both xk and xk minus 1. So you do need to give two initial guesses to start. Okay, they need to be different so that the denominator will not be 0. Okay, so this is the secant method. It's a variation of the Newton's method. The benefit is, again, is not requiring this second order derivative of f, so potentially it's easier to implement and to do the computation. Okay, so that's for the Newton's method and the secant method, which are we only talk about the case for univariate functions. So the f is a mapping from real number, the set of real numbers to the set of real numbers. But we know that in general, the optimization problem involves the x in a high-dimensional space. So the x here is in a subset omega, which is the omega is a subset of the n-dimensional Euclidean space. So the n can be really large. So in general, what we will do is similar to as the Newton's method or secant method. Again, we start from some initial guess, we call it x0, and then we move on to the next point and we call it x1. The question is how do we move, which direction we should consider to move, and how far we should go, right? So this is something that we talked about earlier. And if we can actually do this, then that means starting from, say, we already got to the point xk, the location xk, and then we'll decide a direction. We really want to go for the decent direction, meaning that along this direction, we hopefully can get smaller function value. Okay, that means we really hope to have xk plus 1 to be less than or equal to f of xk, right? We hope to have this relationship. So once we move to a new point, the function value should decrease, ideally. All right, so to do that, then we have red xk, and we decide the direction dk, and then we go along the direction dk with step size alpha k. So this will be the update. We'll compute the xk plus 1 using this. And now you can see if we're really going a good direction with reasonable step size, then we hope that this has a smaller function value than the previous step. Okay, this is a general approach, and most of the algorithms will be the key of most algorithms, of measuring algorithms, is to determine this direction and also this step size. Okay, once you know these two, then you can just keep moving using this iterative scheme, and then you will get to the optimal solution. So this is actually the general idea of most algorithms, numerical algorithms, or measuring algorithms. So the questions, as just mentioned, the question is how do we find decent direction? Well, a very popular choice of decent direction is the negative gradient of f at its xk. Okay? The reason is, remember we mentioned that in calculus you know that gradient f at a point xk. So let me draw a picture. So again, this is a level set, and say we're at, so this is another level set. So let's say this is the function value. These are the contour where the function takes the value takes the value 10, and then this is the contour on which the function takes the value 5. Okay, so now suppose we are at some point here. So this is my xk, and I'm going to go from here to a better to the next point. So say this point is x star. This is a true solution, although I don't know where it is. I'm trying to get there. Okay, and then suppose we are at here. The gradient of f at this point will be the fastest increase direction. What do you mean by that is, you think that's in 2D case, the point is on this plane, is on the screen, and the third direction, which is popping up out of the screen, is the function value, direction of the function value, or axis of the function value, and it is supposed to be a surface. And you can somehow imagine a bowl shape surface where the bottom is facing, where its opening is facing you, and the bottom is facing the is pointing inside the screen, because this is a low value, and you can see the ball is facing, the opening of the ball is facing you. So the gradient of the function at this point is the fastest increase direction, which is this. Okay, so that's the gradient f of xk. Okay, but remember that this is the fastest increase direction. This direction will be the fastest decreasing direction, which is negative f at xk. So since we're trying to minimize the function value, we want to make the function value smaller, so we should go descent direction, and that's why this direction, the negative gradient f at xk, is the most common choice for the descent direction. So when you choose the D, you choose this one. Usually it's a good choice. Okay, but it's not always good. Let me give you an example. So again, let's see a bowl shape function. So it's again defined on two-dimensional Euclidean space, and the contour or the level set looks like this. Okay, so again, the center, this is the minimizer that we want to get, and this value on this contour, on the outside contour, the function takes value 10, and here maybe it takes value 5, here next takes value like a 2, for example. Then again, this is the bowl shape, and the bottom of the ball, again, the opening of the ball is facing you, and the bottom is facing inside the screen. And so say we are starting from here, and then we'll look at the gradient direction, which is, gradient direction is always perpendicular to the contour, to the level set. So it's perpendicular to this level set, because on this level set, the function value stay unchanged. So this perpendicular direction gives you the fastest increase, and this gives you the fastest decrease. So if we use the descent direction, we use this as the descent direction, then we'll go this direction for some step size. And say we reach to this point, and then I'm going to decide the negative next descent direction, which will be negative of the gradient, which will be pointing to this direction. So it seems that I'm going this like a zigzag direction. Every time the direction is perpendicular to the level set contour at that point, so I'll get a zigzag. So although it's not really far from the true solution, but I take a lot of zigzag directions, and eventually it take a long time to get to the x star. So in this case, we're using the negative gradient, but it apparently is not a good choice. Okay, so this happens a lot in practice when the function is not really formula is called, it's not really well conditioned, then we could face this kind of issue. So in this case, the negative gradient direction is not always good, and instead, maybe you want to change the direction in some way so that it can get to the minimum value as quickly as possible with just a few iterations. Okay, so that's a very critical issue that we're going to talk about in details in this class. So that's one. And the other one is, once you decided the descent direction, how far you should go. Okay, remember that even you decided a good direction, but you cannot go too far. Say from here, you go this direction, but you go too far, then the function value may increase. You will miss the minimizer. Okay, so the step size is also important. And the step size, one way to determine the step size is to remember, previously we talked about that if we start from some point, xk, and then we decide the direction, then along this direction we will have a univariate function, because it's like a cut or cross section of the surface, and then we actually get a curve. So along this curve we may have increase, decrease, something like that, and then we want to determine how far we should go along this direction, so that the function value can be as minimal as possible. So in this case, we will define this phi function. This is something we have defined before. And once given the point xk and decided the direction dk, and then the step size is the only thing that we want to find, and that's this phi is a function of that step size alpha. When alpha equals to 0, as you can see, the right hand side will be just f of xk. That is where we are originally at, the function value at xk. And when we change this alpha, we gradually increase alpha, then we actually are gradually going along this direction. So we want to choose a proper step size. Don't go too far, but don't go too small either. So in this case, that's we're trying to find this alpha, which is step size for this univariate function, for this phi of alpha. So the good thing about this compared to the original function f of x is that the x is in a high dimensional space, but this alpha is just a real number. So conceptually, it should be easier to do. Okay, so this is the one way to choose the step size. We find the step size so that the function value is minimized along this direction. Okay, it's minimized along this direction. So in this case, maybe we'll stop here. We'll stop here and then try to move to the next point from there. Okay, so that is also a very common choice, but it's not always good. The reason is if you really want to find the minimizer for this line search function, this is what called line search function. It's to be minimized so that the minimized alpha tells us how far we should go, step less. But if you really want to solve this, although it's a univariate function, then we'll see that trying to find the critical point is not that easy, because trying to find the critical point of this phi, we need to take the derivative and set it to 0 and solve for this alpha. So let's see what happens when we take the derivative. We have done this earlier. If we take the derivative of this function phi, then we'll need to apply the chain rule to the right hand side, and then we'll have gradient f at this point times the derivative of the alpha of inside, which gives us the decay. So the phi prime of alpha is actually this. This is something we have done earlier. And as you can see, if we want to compute this, I will need to compute this stuff, which is still the gradient. And in this case, trying to find alpha that makes this equal to 0 is not easy either. It's not very easy, right? And also, if you want to make sure that the alpha you find is a minimizer or local minimizer, then you also need to check the second order derivative, which gives you this. And in the middle, that's the Hessian matrix. Okay, you need the second order derivative. So they can be very expensive to compute. So that's why, although line search is a very natural choice, but in practice, people seldom do this. It's rarely to really minimize this. Okay, instead, they probably just find some very simple and cheap way to compute alpha. Although alpha is not optimal, it's not really the minimizer of this line search function, but it is usually good enough for the algorithm to run efficiently overall. Okay, so as I said, if we do this very general step of optimization, like update your xk by going along certain direction with step size alpha k. If you do this, then we usually see we usually need to decide which direction dk to choose and what is the alpha we should choose. So this is the key in most of the optimization algorithms. Okay. Okay, now we'll start with the first type of algorithms in this class. So it's called a gradient method. So as we mentioned earlier, the gradient method is in general, it is a descent algorithm written in the following form. So suppose we're trying to minimize. The function f of x. let's say that there is no constraint at all. So let's say it's in Rn. And the gradient descent algorithm or gradient-based method is a special case of the descent method, which is the one I'm writing here. Remember that at a given point in xk, we want to decide the dk, which is the descent direction, and also the step size, which is alpha k, so that by updating this xk in this way, I'll get the xk plus 1. Okay, and then moving from xk plus, I'll go from xk plus 1 to the same thing, decide a new direction, descent direction dk plus 1, and a step size alpha k plus 1, I'll get to xk plus 2. Okay, the gradient method is a special case of this, where you always choose this dk as the negative gradient. So for notation simplicity, we do not write a gradient f, always write a gradient f of xk, but we just write this gk. So the gk means the gradient of f at xk, okay, just for notation simplicity. And the descent direction is set to the negative gradient direction, so it's set to negative gk. Okay, so if we do this change, then this one will be just negative gk. Okay, now we decided the direction, which we'll decide to go for the negative gradient direction in every iteration, and the only thing left to do to find out is the step size. So we try to figure out what is a proper step size to minimize the xk, to minimize the function f. Okay, so remember that a very easy way or very natural way to find the step size is to define this line search function, right? This phi alpha is exactly the same one as we had earlier, but in this case, since we already decided to go for negative gradient direction each iteration, so this plus alpha dk becomes the minus alpha gk. Okay, minus alpha gk, and then the only thing that we need to figure out is this alpha, how to choose this alpha. So this is the line search function phi, and it's a function from the set of real numbers to real numbers. So the alpha is a real number, and you get a real number by plugging alpha into this. So it's R to R. And if you have this phi function, we can take a Taylor expansion. The Taylor expansion if you write the Taylor expansion, remember that it should be phi of alpha equals to phi of 0. I take a Taylor expansion at alpha equals to 0, then we'll have phi of alpha plus phi of 0, and phi prime of 0 times alpha. And then there will be higher order terms, which are, I write this as O alpha. So this is like the terms related to evolving alpha square or alpha cubic, alpha cube, so on and so forth. But now, remember the alpha phi of alpha is this function. So on the left-hand side, this will be equal to that. And when I evaluate alpha at 0, as I mentioned, if you plug in alpha equals to 0, the right-hand side of this becomes f of xk. So that means these two are equal. Okay, and the next one, we take the derivative of f of phi with respect to alpha. Remember we showed this earlier. The derivative of phi with respect to alpha gives us negative gradient, gradient f of xk minus alpha gk times the derivative with respect to alpha of the inside. That gives me gk. So it will be gk and negative gk actually. So I put negative in the front. So remember that this is dot product. So this is the vector. Right, this is n-dimensional vector. This is also n-dimensional vector. So actually, I need to make a dot product between them. or inner product between them. I sometimes write this first one with the transpose so that the column vector is transposed into a row vector and multiply to the next vector, and I get a number. So either way you like. Okay, so now let's see if I plug in alpha. If I substitute alpha by 0, I plug in alpha equals to 0. Then on the right hand side, I'll have this as 0. So this will be negative f of xk. This whole thing will be negative f of xk. But remember that the negative f of xk will use the shortcut gk. So this is essentially just gk. It's the same one as this one. So I have negative gk times gk. So the inner product of the vector gk with itself is just the squared norm of gk. Okay, so this is essentially just giving me negative gk norm squared. Okay, so that's why this is just equal to this. The reason is this one here is just negative of this. Okay, so by Taylor expansion of this line search function, I will get that. I'll get this. And it's obvious that, let me erase this other stuff. So it's obvious that this will be my new xk plus 1. So on the left hand side, I'll have the new function value, the function value f at xk plus 1. And on the right hand side of this, so if I want this f of xk plus 1 less than f of xk, it's easy to accomplish because this part will be greater than or equal to 0. It's not negative. So if I choose alpha small enough, this should be smaller than or equal to f of xk. The reason is this term will be negative, and this term is relatively much smaller than this term because it's little o over alpha. Right? So this term will be dominated by this term, but this term is negative here. So that's why this will be less than or equal to f of xk. Okay, so if alpha is sufficiently small, then we should have alpha k plus 1 less than or equal to f of alpha f of xk plus 1 will be less than or equal to f of xk. All right, so this is the basic idea of gradient descent method or gradient method. Why we call it the gradient descent is because we're using negative gradient as the descent direction. So, and since we chose the negative gradient direction, it's guaranteed to be a descent direction since this term together is negative. We're getting smaller function value. Okay, so this is the algorithm. As we said, every time if you want to run this algorithm, you just choose an initial guess, throw in an initial guess, and then use this formula to generate a sequence of xk's. And in each iteration, you decide the negative gradient as the descent direction, and choose a alpha step size alpha k properly. Hopefully you can get to the optimal solution. So how do you actually choose this alpha k? So there are several different ways to do this. The first method I'm going to introduce is called the steepest descent method, which is actually trying to minimize the line search function. So remember that you have, if we decided to, so we're at xk, and then we decided to go negative gradient direction as the descent direction, then the only thing that we need to figure out is this alpha. So define the line search function phi alpha to be f of xk minus alpha of gk. So as we said earlier, this line search function could be like this. Okay, when alpha equals to 0, then this value here is just f of xk. And if the step size is small enough, the function value will decrease. But for alpha very large, then it's not sure, right? It could go along this direction. So this is the cut I mentioned. So it says this is the x star, and this is the current xk. And you decide to go the negative gradient direction. So this is a negative gradient direction. Then going along this direction, you look at the function value. Starting from here, you go along this direction. And you see the function value is going like this. Okay? So this is what happens when you go along this direction, the function value along this direction will change like this. So initially it will decrease, as we showed in the previous slide. But for long term, it's not necessarily true. And if you want to decide which steps that you should choose, then it seems that this will be a very good choice. This will be a very good choice. So that means we need to minimize this line search function phi with respect to alpha. Okay, we need to minimize this function phi of alpha with respect to alpha. But the phi of alpha is just this, right? It's actually defined in this way. So that's why the steepest descent method is to find the step size that minimize the line search function phi in each iteration. Okay, so that's the steepest descent algorithm. But in practice, how do we really find this, implement this? The alpha k, since this alpha k is minimizing this phi function, right? So we can use the Newton's method we introduced previously. So we treat this phi as a function, and we know that's function from R to R. So it's a univariate function, and this, ideally in principle, the Newton's method can be applied. But as we mentioned earlier, if you do Newton's method, we'll need the phi double prime of alpha, which is pretty expensive to compute, since it involves the Hessian matrix of the f. So that's difficult. But computing the first order derivative, phi prime, this should be straightforward. It's just the negative f times it's just negative gradient f times the g. Okay, so that is straightforward to compute. And if we only know how to compute phi prime, we can apply the secant method. Okay, because the secant method only requires the first order derivative. Okay, so this is the idea in general. Okay, so let's see that we're using the steepest descent method as I introduced here. So we're always trying to, for each fixed xk, for each given xk, and we compute this negative gradient direction, and then we apply the secant method to minimize this with respect to alpha, to find the minimizer alpha, and we call it alpha k. Okay, and that will be the step size. And once we decided that alpha k, we can use this to move to the next point xk plus 1. So a property of the steepest descent algorithm is that if we go from, let's say this is the xk, so we go from xk, we move to the next point xk plus 1 using the steepest descent method, then we can go to the next point from xk plus 1. And the next point will be called xk plus 2, right? So the property of the steepest descent algorithm, or this steepest descent method, is that if you look at the next point or the next direction you're going to go is actually perpendicular to the previous direction you go. Okay, so that's actually not difficult to show, because remember that every time you're choosing the negative gradient direction as the descent direction. So this direction here is just negative gk, and this direction here is negative gk plus 1. Okay, and what we're trying to show here, or what this proposition is saying, is that this gk and gk plus 1 are perpendicular to each other. So they are perpendicular to each other, meaning that the inner product between them is 0. Okay, so why this is true? The proof is given below. This is a line search function, and according to the definition of the steepest descent algorithm, the alpha k is chosen as the minimizer of this phi alpha. Okay? So because of this, we know that alpha k is a minimizer of this. So the derivative of phi at alpha k must be 0, right? This is the first order necessary condition for alpha k to be minimizer of this phi. So the phi prime will be equal to 0. And phi prime equals to 0 if I compute the phi prime and plug in alpha equals to alpha k, and I will get this. Right? This is something that we have done for several times. And now you can see this first this point will be the point xk plus 1, because this is the where we're going to move to, right, from xk. And this is xk plus 1. That means the whole thing here is gk plus 1. Okay, that shows that gk plus 1 and gk are perpendicular to each other. Okay, so once we have this is already, we already got the key. To show this quantity is very easy, because this, according to the updated rule, xk plus 1 is equal to xk minus alpha k gk. Right, this is our gradient descent update. So that means xk plus 1 minus xk will be negative alpha k gk. And similarly, xk plus 2 minus xk plus 1 will be negative alpha k plus 1 gk plus 1. So the inner product of these two, the inner product of the two differences will be just the product of this. But we have shown that this is just 0. So that's why these two are perpendicular to each other. Okay, so this is the property, special property of a steepest descent algorithm. Every time you go along the every two steps have perpendicular directions. Okay. The next property of the steepest descent method is that if you apply this, and anytime that you found your gradient is non-zero, then the next iterate is guaranteed to have a strictly smaller function value. So again, we have xk. We started from xk and we go along the negative gradient direction, and we use the line search to find the smallest, to really minimize the line search function, which means we're using the steepest descent method. Then it shows that the next point you reach to is guaranteed to have a smaller function value than fk. Okay, and again we're applying, we're using the property of this phi alpha. So the phi alpha is a line search, and if we take the derivative with respect to alpha and set to 0, we know that this it will be just negative gk squared. So negative gk squared, as long as gk is non-zero, this negative gk squared will be negative. It's strictly negative. Okay, will be strictly negative. So imagine that we have this. We again have this line search function. And here, the function value itself is f of xk. But the derivative there is negative gk squared, which is strictly less than 0. That means here the derivative is strictly less than 0. The slope is strictly going down, right? And so the function should, at least locally, should go down like this. Maybe eventually it will increase, but it must decrease somehow before it increases. Okay, so let's say this case. But in any case, if we go along this direction for with the negative gradient direction, then you must reach to some lower value. Okay, so let's say this is the new lower value. This is the lowest point where we will have this alpha k, And then this new point will determine the f of xk plus 1, which will be strictly smaller than the f of xk. Okay, so you treat this function here as phi of alpha. So the phi, what it says is the phi of alpha at k, alpha k will be strictly smaller than phi of alpha at 0, alpha equals to 0. Right? So that, and here on the right hand side, the phi of 0 is just f of xk. On the right hand side, left hand side, the phi of alpha k is just f of xk plus 1. So you can see the strict decrease or strict reduction of function value by using the steepest descent method. So the question, you may ask, what if the gk is equal to 0? Okay, in this case, we will not have strictly less than 0 because this gk will be 0 here. Well, if gk is 0, remember that gk 0 tells us that the xk satisfies the first order necessary condition. So if gk is 0 there, then the xk could already be a local minimizer, but it can also be a local maximizer or setter point. But at least when gk equals to 0, we know that we're reaching to something interesting. Okay, so xk will be something interesting. It could be just a local minimizer. So usually when we deal with, we'll apply some gradient descent method in practice. When we find that at some point with the gradient equal to 0, we'll usually stop, because usually there's no guarantee to have even better point. Okay, so that's all for, actually that's the core idea of steepest descent method, and there are some practical issues we mentioned earlier. One of them is called the stopping criterion. Right? We know that you throw in initial guess x0, you run this algorithm, but you cannot let it run forever. You will ask it to stop sometime. So how do you stop? In practice, you ask the algorithm to stop when the gk, the norm of the gradient, is really small. Okay, remember, if it's equal to 0, then we usually just stop. So if we cannot reach to 0, but it's really small, and then we can also stop there, because we spend more time on that, and it doesn't necessarily improve the solution that much. So we probably just stop there. So the first type of stopping criterion is that you set this stopping or a tolerance. The epsilon is usually called the tolerance, which could be a very small number, say 10 to the negative 3 or 10 to the negative 5. If the norm of your gradient is that small, it's even smaller than the tolerance you set, then you can stop. Okay. Another way is, if you don't want to compute the gradient, well, anyway, you'll compute the gradient. But if you don't like using that, then you can try to plug in your function, you plug in your iterates into the function and check the function value. If the function value of the next point, or the point xk plus 1 and the function value at xk do not differ that much, they are very similar, their difference is less smaller than the tolerance you set, then you can stop. And also some people use this, just check how far you went from xk to xk plus 1, and if that is really small, then you stop as well. Okay, so these are popular choices. But usually people prefer to use more relative quantities. The reason is, if you only check the function value f here, if the f is started with some value like 10,000, a million, those things, and you see that their difference is less than 10 to negative 3, then you say it's really good, right? Because you start with a very high value, but you keep decreasing it, and the difference is not that much, you say it's good. But say the function f is originally just like 0.2 or 10 to negative 2, or even 10 to negative 3, then the difference here, if it's 10 to negative 3, it doesn't mean much, right? So what is most important is the relative difference that you make. So this is the common choice. So you check the difference of these two function values of these two iterates and divide it by the previous function value. If this is small enough, say it's less than 10 to negative 2, then that already means that your progress or the relative change is less than 1%. So that seems to be really small, and you probably should just stop. So it's not sensitive to the actual value of f anymore, because you actually normalize this by this denominator here. So similarly, instead of using the absolute difference, you can use the relative difference between the next iterate xk and the previous iterate, the next iterate xk plus 1 and the current iterate xk, because their relative error is, or relative change is small enough. Okay, so let's take a example. So let's say we are trying to minimize this function f, as defined as a function of three variables x1, x2, x3. Okay, so x is in R3, and x has three variables x1, x2, x3. So the function is defined in this way. You have x1, x2, x3, then you get this value here on the right hand side. So let's say we apply the steepest descent algorithm with the initial x0. Then remember that in each step, the steepest descent algorithm will move from the current point xk along the direction of negative gk. And the step size is chosen to minimize the function value along the direction negative gk. Okay, so it seems that the gradient will repeatedly use the gradient. So let's compute it first. The gradient f will be just stacking the partial derivatives of f with respect to the three variables. So the partial derivative of f with respect to x1, as you can see, the three term on the right hand side, only the first term involves x1. So take the derivative with respect to x1, we'll get 4 times x1 minus 4 cubed, which is this. Similarly, take a derivative with respect to x2, we'll have 2 times x2 minus 3, which is this. And similarly, the last one, this partial derivative with respect to x3. So this is gradient. For every given point x, the gradient of f is this. Okay? So at least we can easily get a critical point in this case, because we can just set it to 0 and solve for x1, x2, x3, and that is the solution. But let's say that it's a general problem that we cannot easily tell the critical point from the gradient f equals 0. So let's try to apply the steepest descent algorithm or steepest descent method to solve for this point, to make this gradient f equal to 0. Okay, so let's see what happens in the first iteration. We will start from the initial guess. This is the initial guess given by the problem. It asks us to start from here. Okay, so this is the initial point. And to do the gradient descent, remember that this is x1 equals to x0 minus alpha 0 g0. And g0 here is negative gradient is gradient f at x0. So we already know what is gradient f. You just need to plug in x0. Okay, so that's what I have in the second step. The g0 is just the gradient f at x0. I just need to plug in x0 into the gradient, the formula of gradient here. So just plug in this 4 to negative 1 into this. Okay, 4 to negative 1 into here. And then we will compute the gradient, which is this. Okay, so we decided the gradient, and next we need to determine the step size alpha 0. So according to the definition of steepest descent method, this alpha 0 should be the minimizer of this line search function. And this line search function here is this, let's say this is phi of alpha. Okay, and so we need to plug in this. This is something already computed above. This is something we will compute above. The only thing that is undetermined is this alpha. So we keep this alpha here and plug in this x0 minus alpha g0 into the function f. Okay, so that means here we can compute because we already have x0 or have the g0. So it's just this minus alpha times this and plug into the function f in the previous page. Then we go actually get this. So this is the function of alpha, right? As you can see, this is the function of the scalar alpha. And we want to find the minimizer with the minimizer alpha of this function. So we can apply the secant method. So this is the function that you can apply the secant method. And apparently you're going to do this by using computer rather than by hand. So apply this secant method to this. You will find this alpha 0. This is this value will minimize this. Okay, so this will be the alpha 0. So once you have the alpha 0, you have all the components you needed to compute the x1. So you just plug in x0 here, and the g0, which will be here, and the alpha 0 is here. So just plug in them, and you get next point x1. And it turns out that the x1 equals to this. So that's the first iteration. So remember that this will take some inner iterations because you cannot really find this alpha 0 in the closed form. Instead, you have to use the gradient. You have to use the secant method to do some iterations to find out this alpha 0. Okay, so what happens is this phi alpha is this is the line search function. When x equals to 0, this will be the function value, f of x0. So we initially go down, and then eventually you'll go up. So how far it should go and what is the minimum point? You actually need to solve for the minimizer of this line search function, f, and line search function phi. And then we got this value here, which is from the first previous page it's very close to 4 times negative 10 to negative 3, right? That's approximately just here, this point. Okay, so that's just the first iteration. So once we got x1, we need to repeat the same procedure to get x2. So remember to apply the same update rule. We're going to need to compute this, compute x2 using this. So again, x1 is the point we just obtained, which is this. And the g1, just plug in the x1 into the formula of gradient f, we'll get this. And then the alpha 1 needs to be found by minimizing this. So we know x1, we know g1, and we keep this alpha unknown and plug into the function f, we'll get this. And then we'll apply the secant method again and to find out that alpha 1 needs to be 0.5. Now once we know that, we will plug into this formula. We know this, and this. We can get the x2, which is this value. Okay, so this is a line search function, how the line search function looks like. And from that we should get to the 0.5 as our step size in the second iteration. Okay, so you just repeat this for the third iteration. You will get the x2, you will get the g2, and you will compute the alpha k using the secant method, which is this. And when with this, you get to the new point x3, which is that. Okay, so this is getting closer and closer to the true solution we wanted, because previously we showed that the true solution is this, right? 4, 3, negative 5. So now, after 3 iterations, we're here, okay, pretty close. Okay, this is the line search function for the third step, that's for alpha 2. Now let's consider a special type of function and try to apply the steepest descent algorithm or steepest descent method to it. So it could this kind of function is called quadratic function. It's a analog of the quadratic function for universe for a single scalar, but what is special here is that the function f of x, and x is a high dimensional vector. Okay, so this type of functions are written in general in this way. Okay, in this way. So why we call it quadratic? So you can see on the right hand side, I have x transpose ax minus bx. So the second term is pretty easy to interpret it. So b is a vector with the same dimension as x. So this b times x, b transpose x is just the inner product between the two. You get a number from it. This first term is x is a column vector. This is the matrix A. And this is a row vector, since I take a transpose of x. So it's like a row vector, matrix, a column vector. So in this case, you get a scalar of it, right? You get a scalar of that. Also a scalar here. So it's a difference of two scalars. The reason we call it a quadratic function is that this term is like the second or the quadratic or second order term, or a polynomial of x. I would say a polynomial of x with degree 2. This is a linear function of x. Okay, so the matrix A is n by n, where n is the dimension of x. N is not necessarily symmetric, but we can make it symmetric. So to make this quadratic function in a standard form. So how do we do that? Remember that this is just a scalar, right? It's a scalar, so when I transpose it, it will stay the same. It will stay the same. So when I transpose it, what happens is, when we take the transpose of this, transpose of the, if you have a vector, matrix A, matrix B, you have more of them, say matrix C. You take the transpose of them, that will be C transpose, B transpose, A transpose. Right? So you know this. And now if you treat every one of this as a matrix, so you have a row vector as a row vector, a matrix, and a column vector. You take the transpose of this, and you have a row vector, column a square, and a column vector. So what you get actually is x transpose ax. You take the transpose, you'll be x transpose, which is this one, and then A transpose, and then the x transpose, which is x itself. And I know that this value on the other hand is the same as x transpose ax, because this is just a scalar. You transpose it or not, it stays the same. So this tells us that this is just equal to this. Okay, so since these two are equal, we know that x transpose ax is the same as x transpose ax, and also x transpose a transpose x. So I add them together and divide it by 2, because the two numbers are the same. By doing this, I'll get the same value, right? So this value will be just the sum of itself and this, but these two are the same, so I sum them together and divide by 2. That's why I got this. Okay, so the x transpose ax is nothing but this. So now I have one half outside, and I have this matrix I call the Q. And you can notice that this Q matrix is symmetric, because Q is just A plus A transpose. Even if A is not symmetric, the A plus A transpose is symmetric. You take the transpose, it will be the itself. Okay, so this is standard form of a quadratic function. It could be written as this at the beginning, but it is easy to transform it into this standard form with this Q, with the symmetric Q here. The way to do this is just add A and its transpose, and to form this Q, and they put one half outside. Everything else stays the same. Okay, and with that, it will be easy to show that the gradient of f, we take the gradient with respect to gradient of f with respect to x, you get qx minus b. You take the Hessian, you take the derivative or gradient with respect to x one more time, you get a matrix, and that matrix is just q. Okay, it's similar to the, it's analog to the quadratic function. You have, if I have 1/2 times qx squared minus bx. See, my fx is a univariate function, where x, q, b, they're all scalars. Then the derivative of f will be just qx minus b, and then derivative of f, second order derivative of f of x will be just q. So it's similar to that. We'll show in more details next. We'll continue next time.